All right, so Unit 5.3 talks about something called internal resistance. And internal resistance is really going to exactly what it sounds like, where there is some resistance which actually is within an electric cell. So a few definitions for us before we go through some examples of this. An electric cell is just a device used to generate electricity. Think of it as a battery. Um, in the reading, it talks about there's a few different types of cells. But just for the most part, anything that's a cell is just like a power supply or a battery. Second is something called electromotive force. Now, this can be confusing because there's not actually a physical force that's pushing things necessarily, but this is related as EMF or shorthanded as EMF, and we symbolize it with this curly E here, and it's the total energy per unit charge supplied by a source. And really, it's just a fancy way that it's the total voltage in a circuit, and this will make sense as we go through some examples. Lastly, then, internal resistance is simply the idea that electrical resistance of a cell, so a battery, right? So a battery has resistance in it associated with the electrical reaction. And if you've ever held like a battery, like after you've been using it in a device, you actually have some warmth or some heat being produced from that battery. It feels warmer. And that's because it gets hot when the device is on. And that's because basically there's a small, tiny resistor inside here that is producing heat in it. So it's using some of that energy that it's actually producing. So if this is a 1.5 volt battery, that's what a AA actually is, 1.5 volts. So my EMF would be 1.5 volts. But as we'll see, when I actually hook it up into an electrical circuit, I'm not going to be able to provide 1.5 volts because I'm using some of that actually is heating up the battery. So let's do an example of internal resistance and kind of see how this works, okay? So I'm going to draw a physical battery here just to give us a visual of what's actually happening. This is our cell. So normally we would just draw something like this, but now we're going to have this internal resistance, which we're going to symbolize with little r. So little r is the internal resistance. We're going to hook that up into a light bulb or a resistor or any other major circuit. And this would be R. So what we would do is, again, if we have a switch here, let's add a switch to our circuit. If our switch was open, we could have a voltmeter here, and we would be able to measure the EMF. So if the EMF of this is, let's say, 9 volts, right, we would measure 9 volts when our switch is open. Now, when we close our switch, we're going to have current that's going to start flowing through our circuit, right? So we're going to have a current that's flowing through, giving off voltage to our lamp and then coming back through. But we're also going to have a current flowing through our battery, and so we're going to lose some voltage through our internal resistance as well. So think of this now here. This is 9 volts provided by the battery. If we were to measure the voltage here across our lamp, maybe we get a voltage here of 8.75 volts. Well, that means, again, because of Kirchhoff's loop rule, we have to have some other voltage here. And so our voltage here across this resistor would be 0.25 volts. So what we can understand is really this resistor is just a resistor that's in series with this light bulb. And so as I go around my loop, I'm going to gain 9 volts from my cell. I'm going to lose 8.75, and then I also need to lose 0.25 volts here. So this voltage now here would just be 8.75 because it's accounting for the loss that we have here. So while my battery itself is 9 volts, I'd really only be getting 8.75 volts out of this. So you're going to see an equation that looks like this. EMF equals I times R plus R. And to understand this, this is my internal resistance, and this is my total resistance of the circuit. Remember, resistors in series are going to simply add together. No matter what type of circuit we have, the total resistance is going to be in series with my internal resistance, and that's because you can't have a parallel with this, and we're going to multiply our current. So if we work through this, right, I times little r would be the voltage of the internal resistance, and I times big R would be the voltage of our total resistance. And we're using that by Ohm's law, which is R equals V over I. And then we're just rearranging for V equals IR. So I can replace IR in terms of V. And understanding that this is my voltage resistant of my internal resistance, my voltage of my total resistance, and both of those combined equals my EMF. So again, voltage of the internal resistance plus voltage of the total resistance, that is my EMF. Okay? One thing we don't have to worry about is that because these are in series, the current going through the big resistor is going to be the same as my current and my internal resistance. So those two I's are the same. And we can solve for the power that the battery uses by doing I squared times little r. Oopsie. So that's a way that we'd be able to calculate the power that is lost due to internal resistance by A, solving for internal resistance, and then understanding that I squared times R is going to be that much power. So as we look at this, my EMF equals 9 volts. My voltage terminal is 8.75 volts. So voltage lost in this case is 0.25 volts, right? This is what the battery provides. If I were to measure the voltage at the terminals, which are these two positions here, I'd only get a reading of 8.75 volts. And that makes sense because I've lost 0.25 volts due to my internal resistance. Like I said previously, it doesn't matter how a circuit is set up, whether it's 2 resistors or 3 resistors in series or resistors in parallel, our internal resistance is always going to be in series with that setup. So if I find my total resistance here, this resistor is in series with that. If I find my total resistance here, this resistor is in series with that as well. It's important to understand, though, and remember that because power is I squared R, the current that flows through the battery is going to be different in each of these scenarios. Remember, resistance reduces the flow of current. When I add resistors in parallel, I get a smaller resistance. So this internal resistance would actually produce or use more power because it would have a higher current, whereas this internal resistance would have a less power usage because it would have a lower current. So it's important to understand that the results of these internal resistances will differ depending upon the setup of the circuit.